We'll present to you the co-design approach in cheese with some results on the Seissol and Specfem3D mini application. First, few words about the cheese project. The main objective of cheese is to establish a new center of excellence in the domain of solid earth, targeting the preparation of 10 community flagship European codes for upcoming pre-exascale and exascale supercomputers. I'm not able to switch. Okay, it's good. Here's a quick agenda. First, I will talk about the co-design task within the cheese project. Then I will talk about the ARM ecosystem, and finally I will give you our preliminary results on the Seissol and Specfem mini application on ARM architecture. So for the co-design task in cheese, we are asked to identify and get access to exascale prototype architecture, also to identify applications that are suitable for those prototype application within cheese, and to prepare and run this application to obtain different results. So we are also asked to characterize this application with different metrics. Also to evaluate on the prototype hardware the performance of optimization made during the project in other tasks. And to enrich the different analyses with energy-oriented measure. And we are also asked to do some disseminations or report on our results and material generated, and to be strongly involved with hardware constructor or project, for example, with projects such as the European Processor Initiative, EPY. We base our co-design strategy on 3 levels of application in order to answer the task asked. The first level of application, for the first level of application, we take off-the-shelf benchmark from Montevo, which got us as a mini ghost, for example. Why? Because at the beginning of a project, they are very easy to build, to port, and to run on different architecture. They can be easily tested in simulators. It's also easy to use them to test new algorithm or hardware, and allow to have really quick results. We also define level 2 kind of application, which are mini application. Those are from full application within the cheese project. For the moment, we have mini application for Seissol and Specfem3D. We are aiming to have one from the code HPC. Why mini application? Because they are easier to test on disruptive hardware, easier to test than a full application. It's easy to apply the feedback we get on it on the full application, and they are easier to share with different partners or constructors. And we also define a third level of application, which is the the full application because nothing is better than a real application to have relevant performance measure at scale or large scale tests. For the hardware side, we are trying to cover major constructors and most promising kind of architecture for exascale supercomputer. So we are currently aiming to have results before the end of Q1 on the following architecture. So from CPU Intel with Skylake or Cascade Lake processor to produce result on AMD ROM and also on ARM architecture, which processors such as ThunderX2 or Graviton 2. And from the GPU side, we are aiming to have several results on NVIDIA architecture with V1 and V100 and A100 GPUs, but also to have result on AMD GPU with architecture like the EMI 50 and EMI 100. Here's a quick status of our co-design task. For the moment, we have several results on proxy and mini application, mainly on AMD and Intel CPU. We have time to solution and power consumption on several SKU. We just have first results on ARM CPU, and we will start soon to test AMD GPU. We have more difficulty to have results at large scale for the moment, mainly because your HPC pre-exascale cluster are late. We have also strong collaboration with ARM, a lot of discussion with SIPEARL, which is the company for the European Processor Initiative. And we will start soon a close collaboration with AMD for GPU porting. A good point is that we receive a lot of help from these constructors, as they are currently more challengers than, for example, NVIDIA for GPU or Intel for the CPU side. Now I will talk briefly about the ARM ecosystem. So why ARM? Because it's appeared to be an interesting new competitor in HPC. They are currently first in the top 500 with the Fugaku supercomputer based in Riken in Japan. Fugaku is equipped with a A64FX ARM-based processor. And this system is not only the first one on the top 500 benchmark, but also the first one with HPCG, HPL, AY, and Graph 500 benchmark. So it's sorry. So we can see that ARM is a strong competitor now in HPC with such a supercomputer. So what about ARM in HPC? Sorry. So what happened the last year in the ARM ecosystem? There were several announcements on ARM-based processor from different companies. For example, AWS, also AMPERE, Marvel, SIPEARL. And what we see is that currently ARM start to have a strong presence in the world with different projects and cluster. For example, you have the Astra supercomputer in the US, which is based on ThunderX2 ARM processor. You have also, for example, Isambard in the UK, which is also equipped with ARM processor. So ARM starts to be more and more present in the HPC today, and is a very interesting architecture for upcoming exascale supercomputer. Now some information on the current ARM available processor. First, the A64FX from Fujitsu, which is an ARM-based processor, but with a custom Fujitsu microarchitecture. So it is not off-the-shelf ARM core on the Fugaku supercomputer. As you can see, this architecture, I think it's the first one in the world that supports the SVE instruction set. And as you can see, the processor is declined with different kind of frequency. And it is composed of 4 core memory groups of 12 cores, and have some HBM on it. Sorry. There is also the AWS with the Graviton processor. So currently we have access to Graviton 2, which is an ARM v8.2 processor based on the Neoverse N1 ARM microarchitecture. So on this side you can see few characteristics of this processor, which is not really easy to have. There is not very strong communication on it. There is also currently the Altra processor from the AMPERE company, which is also an ARM-based processor using Neoverse N1 cores with up to 80 cores per processors. So the A64FX from Fujitsu is more HPC oriented, where the AMPERE Altra and AWS Graviton 2 are more server oriented, but this processor give very interesting results also for HPC. A few words of what a lot of people are expecting. It's the RHEA processor from the SIPEARL company, which will be also HPC oriented processor with ARM core. It will be based on the CPU cores, as compute unit building blocks. Those are Neoverse V1 ARM core. It will have HBM and DDR for memory, bandwidth, and capacity. We'll have the latest PCY and CCYX links to interconnect. So for PCI, we can expect to have PCI Gen 5 on it. And it will have low power, low latency links for die-to-die and chip-to-chip connection. As this processor is expected for 2023, we don't have a lot of characteristic to share. We have some, but they are currently on NDA. So for the moment, the specification of this processor is keeping quite secret. Another good point for ARM is the server and HPC development solution that they propose with a compiler which support C, C++, and Fortran, and also a parallel debugger and profiler via ARM Forge. Having such a software environment is really interesting as it helps to port and optimize application easily on ARM architecture. There are also LMVM and GCC that are supporting ARM as a compiler. Now some preliminary results on Cheese Mini application. First on Seissol. Seissol is a scientific software for numerical simulation of seismic wave and phenomena and earthquake dynamics. It uses tetrahedral meshes, also different, it uses elastic, viscoelastic and viscoplastic material to approximate realistic geological subsurface properties and can arbitrarily use a high approximation order in time and space. We don't use the full application of Seissol, but the mini application, which is mainly the same as the full application, but without I/O. The Seissol application is a very mature and well-optimized application, which makes us encounter an issue on ARM because it was using a library optimized for x86, the libxsmm, which was using x86 intrinsic. So we have to use another backend to be able to run the mini application on ARM. So it makes it hard to compare the different architecture because a part of the code is not the same. So here some figures with metrics given by the application. So the first one is on AMD ROM, the second one are on Intel Cascade Lake, and the last one on the Marvell ThunderX 2, which is ARM-based. What we can see is that the results on the ThunderX 2 are not very good, but you have to keep in mind that the code is not quite the same due to the library between AMD, Intel, and the ThunderX 2, and also that ThunderX 2 is kind of old architecture for the ARM perspective. We are aiming to have very soon results on Graviton 2, which must be way better than the ThunderX 2.1. For Specfem3D, so Specfem3D is a code that simulates 3D seismic wave propagation. It's one of the first seismological simulation code capable of processing 3D model on parallel computers, and also is able to handle a multitude of topographies and numerical models, so elastic, viscoelastic, acoustic, etc. Here are first results. So the number of core used can look quite strange, but the Specfem3D mini application require to have a number of processes being a square. So that's why you have only 16 core used on this slide. What we can see is the same as with Seissol, is that the ThunderX 2 ARM processor don't give really good results compared to AMD ROM or Intel Cascade Lake. But when you are looking to the AWS Graviton 2, you see that this processor, which is a server-oriented processor, also give good results on our mini application compared to AMD and Intel. Here's some result with a larger number of cores, so 64. We have quite the same result with the ThunderX 2 not being so great. But when we are looking to the Graviton 2, the result is not as good compared to ROM when using 64 cores as it was with only 16 core used. Just a slide for the future. This is advices to prepare application for the RHEA processor from the European Processor Initiative. There are things that is very important to keep in mind. The first is to test your application on the current available ARM architecture. Why? Just to be sure that you have no issue with compilation or libraries. And for projection to the future, you have the A64FX, which can be good to test SVE instruction set, but you have to prefer no result on Graviton 2 because it will be easier for you to perform projection as the 64FX ARM processor from Fujitsu as a custom micro architecture. So Graviton 2 with Neoverse N1 off-the-shelf ARM core will be closer in terms of behavior to the Zeus core, which will be Neoverse V1 of the shell ARM core. And so RHEA, the SIPEARL processor, will also have a HBM. So a main question today is what will happen if there is no cache mode for the HBM? User can may have a memory allocation issue in the future because memory allocation will have a strong impact on performance. So old work made on Intel KNL in flat mode could be interesting to have because maybe some modification on application on memory allocation will have to be made.